Hello everyone, welcome to lecture 5 in power circuit and electromechanics. So in this lecture we will look at the test for the conservative nature of our system, and the second part is the dynamic of lump system. Okay, so let's start with the first part, test for conservative nature. Now, if you remember, we have this formula to calculate the force or the torque of electric origin. Okay, and we also find out that we can calculate the current if we are using energy function. We can calculate current as the partial derivative of Wm with respect to lambda. Okay, and mathematically we know this: the second order of cross partial derivative of a two variable function should be the same. Okay, to be able to apply the energy method or the core energy method that we use, our system needs to be conservative. In other words, it should be the field, the coupling field should be lossless. And how do we test for the conservative nature of the system? Our system needs to be conservative in order to be able to apply the formula we develop. So that is the condition. Okay, mathematically, our necessary and sufficient condition for the system here, okay, because we only have two variables, so we only have one condition for the cross second derivative. Okay, therefore if we do this, it means that on the left hand side we will do df by dx to get the left hand side here, and the right hand side here we will do di by dx. Okay, so on the left hand side we have here, and we want to have this, so we do d by d lambda. Okay, df by d lambda. So to get this one, so it should be that one on the left hand side. On the right hand side, if we notice this and we do di by dx, then we get the right hand side here. And mathematically, if our system is conservative, then this needs to be satisfied, so we can prove that it should the necessary and sufficient condition should be this. Okay, so after we calculate Wm, we calculate the force and the current. Okay, and then we test this condition. Okay, or if we use the core energy methods, okay, then we have Wm dash, okay, Fe will be d Wm dash by dx, and lambda will be dWm by di. Okay, in that case we do the cross second derivative one more time. Okay, so we do the left hand side df e by di. Okay, and the left hand side we will do d lambda by dx, and we get this condition. So either use the energy method, we apply this, or use the co-energy method, we will test for this after we calculate the force and lambda for linkage. So we have here an important example for two electrical and one mechanical process system. So for this system, we know that the core energy will be calculated as lambda di1, lambda 1 di1 plus lambda 2 di2 plus Fe dx. Okay, so three components. Therefore, we have three partial derivative first degree. Okay, the Wm dash by di1, the Wm dash by di2, and the Wm dash by dx. And the condition for conservativeness will be any cross. So we will group this one and this one to form the first condition. We group this one with this one to form the second condition. Okay, and we group this one with this one to form the last condition. So in total, after we calculate lambda 1, lambda 2, and Fe, we will need to test for this condition, and this condition. And once they all satisfied, then whatever we do previously would be valid. Okay. Of course, we can extend this to multiple electrical and multiple mechanical process system. Now, I'm going to introduce the concept of energy conversion between 2 points and then in a loop. So if we remember, dWm can be expressed as I d lambda minus Fe dx. Okay, so we call this one first component plus this one the second component, and the minus sign will be inside the second component. So when we go from A to B in figure 4.31, the change of the stored energy, okay, would be the integration of this between A and B. So if we calculate the first component, lambda will be varying from lambda A to lambda B, and in the second component, x will be varying from xa to xb. Okay, so this integration is simply now defined as EFE from A to B, so energy from electrical. Okay, and this will be notified as EFM, which is the energy from mechanical, and we're going from A to B. Okay, we need a particular path to calculate those value. Okay, so we can apply this concept when we study energy conversion in the device that operates cyclically, and basically all the machine that we will look later will operate cyclically. Okay, therefore this tool is useful. So the device, an electromechanical device, can operate in two modes. Okay, the first one is called motor mode, and the second one is called a generator mode. Okay, so before we do that, before we will be able to determine if a system is operating in a motor mode or generator mode, we need to calculate the energy conversion over a complete cycle. Okay, so this is the integration over a complete cycle. In a complete cycle, our system, if it's operating cyclically, it will come back to the original state. Okay, so we know that on the left hand side, the change of the stored energy will be 0. Okay, that's the meaning when we go over a complete cycle, we return to the original state. Okay, but on the right hand side, we will have an overall over a complete cycle of ID lambda, and the second component is complete integration over the complete cycle of Fe dx minus Fe dx. Okay, so we know that this one is the energy, ID lambda is the energy from electrical, and EDX will be the energy from the mechanical. So basically, over a complete cycle, we'll have the sum of the cyclic of the EFE over a complete cycle plus the EFM over a complete cycle will be 0. So we can say like this: EFE over a cycle plus EFM over a cycle will be 0. So once we calculate it, we can say that EFE over a cycle will be minus EFM over a cycle. Depends on the particular case. It would sometimes it would be easier to calculate EFE, and in other cases it would be easier to calculate EFM. So it depends on the system, but we'll pick the easy one to calculate. And EFE will be the can be used to determine the operating mode of the system. So if our EFE over a cycle is positive, then our system is operating as a motor. If our EFE over a cycle is negative, our system is operating as a generator. It's pretty easy to remember. Energy from electrical. If it's positive, it means that the system is consuming electrical energy, so it should give mechanical energy, and that's a motor. And okay, now if EFE is negative, it means that our system is basically not consuming electrical energy, it's generating electrical energy, okay, and from mechanical energy, and therefore it is operating as a generator. Okay, so that's the first part of our lecture.